All right, this is section 8 point, let's say, additional. This is on common, or say simple, maybe it's a better word, RSA attacks. And so what I want to do is just look at a couple of simple attacks. 3 of them. They're not really useful per se in the sense that they're very simplistic and they've been accounted for, but they form a foundation of attacks that are used, and they give some insight as to why we cannot be sloppy, right? So let's say these are not useful per se, or let's say useful as is. But 2 things, they form a foundation for useful techniques, and they tell us why we can't be sloppy. They show us we must be, let's say, careful with our implementation. So the first one I want to look at is what's called the common modulus attack. There are actually several common modulus attacks, but this is sort of one of the most simple ones. So here's the supposition. Right, suppose there are 2 different Bobs. There's Bob 1 and Bob 2. And suppose they know each other. For some reason they happen to end up using the same modulus, n, but they use different encryption exponents. Let's say different E1 and E2, and suppose those happen to be co-prime. So maybe one uses, they're using simple numbers, so maybe one uses 3 and one uses 7 or something like that. So suppose this happens. So here's the situation. Suppose Alice wishes to send the same thing to both. So she wishes to send P to both. So she does the obvious. She calculates 2 things. C1 is going to go to Bob 1. So this is P to the E1 mod n, and C2 will be P to the E2 mod n. So the first one is for Bob 1, and the second one is for Bob 2. So suppose Eve is the eavesdropper. She obtains both of these, C1 and C2. Now here's the deal. Since the GCD of E1 and E2 is 1, there's a coprime. We can write 1 as the linear combination of the 2. Let's say let's say Eve, because she's doing it. So Eve can find alpha and beta such that alpha E1 plus beta E2 equals 1, property of the GCD. So then she can actually find P. This is because if we take a look at the following way, if she takes C1 to the alpha times C2 to the beta. Remember, she has the C's, she has the alphas and betas. Because she has the E's, she can find that they're coprime. That's easy. She can do the Euclidean algorithm to find the coefficient. That's easy. So she takes C1 alpha times C2 beta. So all this is mod n, and I'll write that at the end. This is going to be congruent to P to the E1 to the alpha times P to the E2 to the beta, because that's what C1 and C2 are. This is P to the alpha E1 plus beta E2. This is P to the 1, which is P. mod n. So she's found P. So the key here is, of course, don't do this, right? So this is a, obviously the chance of this happening is slim, right? Probably they won't use the same n. Probably they'll use maybe even the same E1 and E2. So we won't have a coprime situation. But again, this is just an example, and almost certainly Alice won't send the same P to both. But this is just sort of pointing out that there are some kinks in the armor that we have to be careful. So this is a common modulus attack. Let me clear the screen, put the next attack in. So this is number 2. This is the Hastad broadcast attack. So this is a method which generalizes, but we'll look at the really, really simple cases. Simple case. Let's see, here's the simple version. So suppose that so this is sort of complementary to the previous one. In the previous one, they used coprime E's. But let's sort of flip this around and say, like, well, maybe they use the same E. Now, this may seem surprising, but in the real world, actually, there's a specific E that's used commonly. And so this isn't entirely unreasonable, right? So, but we'll keep it as a simple E. So we're going to suppose there are 3 Bobs. And they will all use E equals 3 for simplicity, let's say. Because this makes encrypting easy. They're only raising things to the 3rd power, mod their own moduli, right? So this is what they'll do. They'll use, let's say they use coprime moduli. Coprime n1, n2, n3. Just so we're clear, this is a pairwise coprime. Which means the GCD of any 2 of them is 1. So here's the situation. So it's the same thing. It's a broadcast attack, which means that Alice is going to send the same thing to all of them. Right? So Alice wishes to send P to all 3. So what does she do? She does the obvious. She calculates the following. She calculates C1, which is P to the 3 mod n1, C2, which is P to the 3 mod n2, and C3, which is P to the 3 mod n3. This is for Bob 1. This is for Bob 2. This is for Bob 3. So suppose Eve intercepts them. C1, C2, and C3. So consider the following system. So I'll put a variable in here. The system will be x is congruent to C1. Now, let me pause to say this. She knows C1 because she intercepted it. It's also true that C1 is congruent to P cubed mod n. She doesn't know mod n1. She doesn't know P cubed. Well, she doesn't know P. She knows P cubed because it's the same as C1. That's all right. So the second one and the third one. So since the moduli coprime, she can use the Chinese remainder theorem to solve this. So by the Chinese remainder theorem, she can solve this. And not only that, she can find the least non-negative residue mod the product. So she can solve this. So just so we remember, she can solve it mod n1, n2, n3. And so she finds So when we did the Chinese remainder theorem, we didn't just find the x, we typically found the smallest non-negative one. So she finds the least non-negative residue x, which solves this. So in other words, i.e. she has x with, in this case, x congruent to C1 and C2 and C3 mod N1, N2, N3. But in the solution, she's got x is congruent to p cubed mod N1, N2, N3, because the Chinese remainder theorem gives a solution that's true mod the product of the three in this case. But here's the fun bit. So here's the deal, is that in this case, each of these p's, and also actually let me say this, also this x satisfies, because it's the least non-negative residue, it's between 0 and N1, N2, N3. So here's the deal. Here's sort of the fun bit. However, P itself is less than N1, P is less than N2, P is less than N3. So the product, or the cube, is less than N1, N2, N3. So what this means, in fact, is that P cubed is actually equal to x. They're not just equivalent mod N1, N2, N3, because x is between 0 and N1, N2, N3, and P cubed is between 0 and N1, N2, N3. So P cubed and x are exactly the same thing. Thus, P is actually the cubed root of x, which seems really funny because x is a very large integer. And so you might be surprised to know that it has a cubed root, but it does simply by the construction here. So what she can do is, Eve simply does this. She literally takes the cubed root. And finds out P. And so that's the Hastad broadcast attack. So there's one more I want to look at. So let me clear the screen and look at that one. So this is sometimes called the intercept / resend attack. And this can be thought of as like a, just be careful what you do with your garbage attack. So suppose that Bob, this is a really nice, kind of cool, simple one. So Bob is going to use NE and ND. So the NE is the public one, the ND is the private one. So here's the deal. Alice wants to send in a message. This is just one person. So she wants to send P. So obviously she does C is congruent to P to the E mod N. And sends it. Right? So B. Eve intercepts this. Now, she can't read it, of course. But instead, what she does is this. Right? So she chooses, let's say, some positive integer. And that positive integer is going to satisfy the GCD of R and N being 1. Now she can do this because she knows N, that's part of the public key. She can find the GCD, that's easy, Euclidean algorithm. So she creates the following. She creates C bar, which is going to be CR to the E mod N. And sends this on to Bob. So, what happens? Bob gets this. And what does he do? He tries to decrypt it. So he takes that C bar and he raises it to his decryption exponent. When he does that, this gives C R to the E to the D, because this is what C bar is. This is all mod n. Again, I'll write that at the end. C is, of course, P to the E. So we have P to the E, R to the E to the D, which is P to the E, D, R to the ED. Now, the ED, of course, is the decryption process, right? So ED is congruent to 1, in this case, for the power. So this reduces to P, R mod n, right? So when Bob sees this, he just thinks it's garbage, because this makes no sense to him, so he throws it out. Maybe puts it in his trash or something, whatever that means symbolically. And so what Eve does is she retrieves it, fishes it out of the trash, and multiplies by our inverse, which exists because the GCD of R and N is 1. And when she does that, say, and thereby gets P. So she's got the thing by sort of decrypting it, or not by decrypting it, by intercepting it, scrambling it, sending it on, and sort of confusing Bob. So the solution is, of course, just like don't leave things lying around in your metaphorical trash can for other people to fish around with, or just be careful, make sure things get deleted, things like that. So these are the 3 attacks I wanted to mention, and that is it.